on. All right, I guess we'll get started. So we're basically finished aggregation and composition. So we're moving into talking about the fourth pillar of object-oriented programming. All right, so you know that, we've talked about encapsulation, modularity, and what's the other one? I had it just a second ago. Sorry. We talked about abstraction, encapsulation, modularity, right? So far, that's what we've covered in the course. The fourth pillar is what's called hierarchy, and that's going to start to show up, if not today, then the next lecture or the next. But this is the lead up into talking about hierarchies of classes. What I'm going to talk about today are interfaces. Right? So we've actually seen interfaces in the class already, right? You know that an interface is simply a specification of the methods that an implementing class must provide. Right? Usually, an interface is just made up of a bunch of method declarations. There's no implementation. Right? So the interface says what methods must exist in a class. It doesn't say how they're implemented. Java actually allows you to implement some methods in an interface. So you are allowed to put static methods in an interface. And you're allowed to include what are called default method implementations, right? And we'll see examples of the second one anyway later on. Now remember that interfaces define a type in Java, right? So you can actually make a variable of an interface type, right? Even though the interface has no, even though an interface on its own has no implementation, right? So for example. Right? I can make a variable t of type list. Right? List is not a class, it's an interface. Right? What can I store in that variable? I can store any object that implements the list interface. Right? So I can put an array list into a list variable. I can put a linked list into a list variable. You can even put your own list class into a list variable as long as your list class implements the list interface. Right? So anybody is allowed to extend the list or implement the list interface, and then you can use that class, your new class, in the way I just showed you. Right? And it's not just variables that you can make. You can have parameters to methods. Right? So if you have a method that takes in a list, right, you can pass it in any kind of list, and the method works. Right? You don't have to program to any particular class's interface, any particular class's API. Right? You can just use the API of list. Okay, now a class that implements an interface must implement all the methods declared by the interface, right? So we've seen examples of this already too. We've implemented comparable for several classes now, right? How do you implement comparable? Well, you say you implement comparable, and then you provide a compare-to method. Right? Okay, so there's another interface that I want to look at today, and it's called the iterator interface. So an iterator is an object that knows how to iterate over a collection of elements or a sequence of elements. Right? So if you have a list or a set, list and set both provide iterator methods that return an iterator. The iterator is able to loop or iterate over the elements of the list or set. Right? Now, you normally don't use an iterator directly. Right? So most programmers will never use, most programmers in everyday programming will not use the iterator directly. Right? The one time you have to use an iterator is if you are looping or iterating over a list or set and you want to remove something from the list or set as you loop. Right? So for example, you might loop over a list and remove all of the negative elements. Right? Or you might loop over a set and remove all the words that begin with A, or something like that. Right? In those cases, you have to use an iterator object. Right? And the list and set notebooks show you how to do this. Right? But normally, you don't use an iterator directly. You do, however, use the iterators indirectly very often. So whenever you write a for each loop, Java is actually using an iterator object under the hood. Right? So the language hides everything about the fact that you're using an iterator. Right? The compiler synthesizes the iterator and calls all of the appropriate iterator methods for you. Right? So that's what the Java is actually doing when you write a for each loop. Right? There's some iterator object that's created. The iterator object loops over the collection. Right? That's what the interface looks like. Right? Remember, an interface is just a bunch of methods. So this one only has 4. 2 of them aren't important to us right now. Right? These are the 2 important ones. So there's one method called hasNext. Right? So the iterator object will return true for hasNext, right? If there's still some elements to iterate over in the collection. Right? So when you start at the beginning of the collection, hasNext will be true. When you get to the end of the collection, hasNext will be false. Next returns the next element in the collection. Right? So if you start at the beginning of the collection and call next, you get the first element of the collection. The next time you call next, you get the second element. Right? The next time you call next, you get the third element, and so on and so on and so on. If you call next and there are no more elements in the collection, then you get an exception, right, to indicate that you've tried to iterate over too many elements. Okay. The way the for each loop actually works is that a for each loop will work on any object whose class implements what's called the iterable interface. Right? So there's actually 2 interfaces that work here. Right? There's iterator, that provides the object that can loop over a collection. Iterable simply says that an object can provide an iterator. Right? So for example, list implements 2 interfaces. Right? The list interface itself implements the collection interface and the iterable interface. Right? The set interface implements the collection interface and the iterable interface. Right? So all that says is that a list is a collection, and a list is an iterable. I guess it's just an iterable. Is an iterable. Right? Now arrays, you can write a for each loop on an array. Right? So for each element in the array, do something. Right? Now arrays are weird. They don't implement the iterable interface. Right? But the language goes out of its way to pretend that they do. So when you write a for each loop on an array, something else happens. Right? But it still works. Okay, the iterable interface only has 3 methods in it. Right? 2 of them we don't care about. The one we do care about is the one that returns an iterator. Right? So any iterable object can provide an iterator. Right? The for each loop uses the iterator object to loop over the elements of a collection, and that's it. Right? So that's how it works under the hood. Okay, now how do you go about, if you wanted to, how do you go about implementing a class that provides an iterator? Right? So the example I'm going to do today is I'm going to try to replicate what Python does. Right? So this is in the notebooks if you've read the interface notebook. All right, so in Python, you can write, if you want to write a counting style loop, you have to make a range object, right? And then you just use the regular Python loop, right? So for I in range 0 to 10, right, do something inside the loop body, right? And inside the loop body, the value of I is 0, then 1, then 2, then 3, up to 9, right? So you don't include the last element in the range, right? And so that's how you write a counting style loop. Now in Java, you have to do like for int I equals 0, I is less than something, I plus plus, or something like that, right? Which is a lot more verbose, right? You have to write a lot more to get the same thing done. So can you replicate what Python does in Java? The answer is yes, but you shouldn't do it. But you can do it, right? So you can emulate the Python counting style loop by cooking up your own range class, right? If the range class implements the iterable interface, then you can write the for each loop like this, right? Which is almost the exact same as what you would write in Python, right? So for each int I in this range, do something with I inside the loop, right? So as long as you write range correctly, this will work just fine, right? Now range here is more or less the range class that you have in assignment 3, right? More or less, right? The assignment 3, you don't have it doesn't implement the iterable interface, right? So what's a range? Well, it's got a minimum value and a maximum value, right? So here's the range class, right? So I want a range class that implements the iterable interface, right? If I do that, then that makes range objects a target for a for each loop, right? So that is, I can write a for each loop using a range object, right? What does the range have? It's got a minimum and a maximum. Here I'm calling it start and stop, right? Because I'm making this class especially to implement a Python style counting loop, right? Now this range class is not very flexible, right? This one always starts counting at 0. Sorry, no, it doesn't. There is a second constructor. So this one, it's got 2 constructors, right? So the first constructor, you only set the stopping point, right? And then it assumes you're going to start counting at 0, right? So 0, 1, 2, 3, 4, 5, up to stop -1, right? The second constructor actually takes in 2 arguments, so now you can specify the start and the stop point, right? You got to do some input checking first, right? If the stop is less than start, that doesn't make sense, right? So we'll throw in a legal argument exception, right? Start can be equal to stop in this case, which is fine. That's the empty range, right? And then you just set this start and this stop to start and stop, right? Which is what you should have done in the assignment as, also. Okay, so I said that the class implements iterable, so I have to provide the iterator method, right? So I override the interface's iterator method to provide my own, right? What does this method return? Well, it returns an iterator over some integers, right? Because the sequence is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? They're all integer values. Right? So I'm going to provide an iterator that can return integer values, right? Now, where am I going to get this iterator class? Well, I have to make my own, because there isn't one that'll do it for me, right? So I'm going to return a range iterator object here, right? All right. Now, that means I have to implement a range iterator class, right? And the range iterator class has to implement iterator, right? And so in other words, it has to be an iterator, right? Okay. So this is the first time you've seen a class inside of another class, right? This is the first example in this course, right? So inside the range class, there's a range iterator class, right? The class is marked private, so this is also the first time you've seen a non-public class, right? Why is it marked private? So if it's marked private, nobody outside, there's no class outside of the range class can see this class, right? So in other words, that means no one other than the range class can actually make a range iterator object or call a range iterator method, right? So only internally will range iterator work as a class, right? We have a class inside of another class, right? In this case, it's called, this is a nested inner class, or you can just say inner class in this example, right? Now those 2 words, nested and inner, mean something very specific in Java, right? Okay, so notice the body is not here. I'm going to show you the body in a moment. Okay, so what's a nested class? So a nested class is a class that's defined inside of another class, right? So when someone says nested class in Java, they mean there's a class inside of a second class. Why would you make a nested class? Well, a nested class exists only to serve the class that it's inside of, right? So range iterator exists only to serve the range class, right? That's its only purpose. Right? If you're implementing a nested class, right, and you decide later on that, hey, this would be useful somewhere else, right, so outside of the enclosing class, right, then it should not be a nested class, right? In other words, you should define it as a regular class or a top-level class, right? So a top-level class is just a class that's not defined inside of another class, so it's not a nested class, right? So that's the general rule, but the Java standard library breaks that rule, right? So if you look at the map class, there's an entry class defined inside of map as a nested class, right? That entry class is public so that anybody else can use it, right? So an entry in a map is just a key and a value pair, right? So there's an example of a class that would be useful outside of map, but is actually defined inside of map, right? Now the reason it's defined inside of map is because map is a collection of entries, right? So it makes sense to bundle the entry class with the map class. Okay, now iterators in general are normally defined as a nested class, right? Because it doesn't make sense to have an iterator without its enclosing class, right? So in other words, it doesn't make sense to make a list iterator if you don't have a list, right? What's it going to iterate over, right? It doesn't make sense to have a range iterator if you don't have a range object, right? What's it going to iterate over if it doesn't have an enclosing class? Okay, now what is an inner class? So remember, the iterator class is a nested class, and it's an inner class. Okay, so a nested class is an inner class if it's not static. Right? So there's a keyword. You can mark a class as being. You can mark an inner class as being static, and we'll see an example of that in a week or so. Right? If you go back to if you go back to here, right? The declaration for range iterator does not have the word static in it, right? So it's not private static class, right? It's just private class. So that means it's just it's an inner class and not a static inner class. Sorry, not a static nested class. Okay. So what is an inner class? Well, an inner class object always has a reference to an object of its enclosing class. Right, so that means every range iterator object has a hidden reference to its range object. Right? Every list iterator has a hidden reference to its list object. Every set iterator has a hidden reference to its set object. Right? An inner class is allowed to access the fields of its enclosing class. Right? So that means a range iterator object is able to access the start and stop fields of its enclosing range. Now, range iterator is defined inside of the range class. So if range wants to, it can go into the range iterator object and access its fields, right? Because range iterator is considered to be a member of the range class, right? So if you have a nested inner class, both objects can access the other object's fields. Right? A range iterator can access the range object's fields. A range object can access its range iterator's object's field. All right, so what exactly is this range iterator going to do? Right? So it's actually very simple. It counts 0, 1, 2, 3, 4, 5, 6, 7, 8 up to, but not including the stop value. Right? So it doesn't necessarily start at 0. If your range is defined as 5, 7, then it'll start counting at 5. Right? So a newly created range iterator object starts counting at the starting value of its range. Right? Every time you call next, right? So remember what next is supposed to do. Next is supposed to return the next value in the iteration. Right? So every time next is called, next will throw an exception if there's no more elements to iterate over. Right? So in other words, if the iterator has reached the end of its range, it'll throw an exception if you call next. Right? Because there's nothing left to iterate over. If it hasn't reached the end of its range, right, then it returns its current count and then adds 1 to the count, right? Because this is all the range iterator object doing is counting. Okay, every time you call hasNext, right, the method returns true if the current count is less than the stopping value, right? In other words, are there still more values in the range, right? Otherwise, it returns false, right? You've finished using up all of the values in the range. Right? So implementing this thing's not hard at all. It's just a counter. Right? So val, that's going to be my value, or that's going to be the value of the counter, right? Just like in the counter class. Right? I've got a constructor. Right? It doesn't matter it doesn't matter what access modifier you give this constructor. Right? The class is already private, so there's no. It doesn't matter what access modifier you put here. The class is still private, so even if the constructor is public, you can't access the constructor from outside of the range class. Right, so I've just left the access modifier off. All right, so the iterator is supposed to start counting at the start value of its enclosing range. Right? So in other words, I want to set the current value to the starting value of the range. Right? Now, you are allowed to reach into the range object and access its field, right? But the syntax is very bizarre, right? You write the name of the enclosing class, right? So big R range, dot this, which is strange, right? Dot start, right? I guess the correct way to read this is backwards, right? You want to, it's this, right? It's this range iterator's range object and the start field belonging to that range object. I don't know why they chose to write it that way instead of writing it this.range.start, because that reads a lot more natural to me, right? But this is the syntax that they chose, right? So that's how you go into the range object and get its start value. Okay, how does hasNext work? Well, hasNext returns true as long as the current count, or value, is less than the stopping value of the range, right? Well, that's easy. So this value is less than range.this.stop, right? Return true. Now, what about next? So next has to throw an exception if hasNext returns false, right? So next is the method that returns the next element in the iteration, right? If there are no more elements, your iterator should throw a no such element exception, right? So that's actually specified in the iterator class, in the iterator interface. Right? The iterator interface says that next should throw that exception, right, if you've run out of elements to iterate over. Okay, now the val is the current count, right? So that's the value I want to return, right? But I also have to increment that count by 1, right? Because I want to go to the next value in the iteration, right? So remember what the current value is, right? Increment the current value, and then return the previous current value, right? And away you go. Right? And that's it. You've now got a range iterator class, and you've got a range object, and you've got a range class, right? So now you can write your little for each loop like that, right? So for int I in new range 0 to 10, print I, for example, right? So what does that do? That just prints out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the range iterator object is just an object that counts in this case, right? And what does it count from? Well, the range object says what it counts from, right? From 0 up to, but not including 10, right? And then you can write your counting style loops like that if you choose. Right? Now the class is sort of flexible. It's not very flexible. It's sort of flexible. Whereas here. Right? So you can, by default, it starts at 0 and goes up to some value. Right? This one lets you start at some other value, some specified starting value, and go up to some other value. Right? What this class doesn't let you do, it doesn't let you count down, right? And it doesn't let you count in steps other than 1, right? Which you can easily do with a counting style loop, in a regular counting style loop, right? So you can count down by changing the update expression, right? You can count in steps of 2 by changing the update expression, right? But you can easily you can easily extend this class so that you can count down and you can count in steps other than 1, right? Either up or down, right? It's not hard at all to extend the class to do so. It's actually an exercise in the notebooks to do that. Okay, question?
What's the advantage to this approach versus the normal one?
There's no advantage. There's actually a disadvantage. So the disadvantage is as follows. Because you have a iterator, Iterator is a generic class, right? So generics in Java, they only work with objects, right? So you can't have an iterator of int, right? You have to make an iterator of integer, right? It's always more expensive to use big I integer than it is to use little I int, right? Because there's all this overhead of making an object and then converting the object to int when you have to do arithmetic and then converting it back to the object when you're done, right? So this method is actually, this approach is actually worse in Java, right? There's a lot of overhead. Well, there's not a lot. There's some overhead in making the integer objects that you're iterating over. So there's no advantage to doing this other than it's slightly easier to write the loops if you do it this way, right? The reason for showing you this is because almost everything we do from here on in is going to be working, we're going to be making collection objects. So we're going to be making our own lists, our own stacks, queues, and lists, right? All of those objects have iterators. So you need to know how to implement the iterator interface. Right. Okay, any other questions? All right, so that's your first exposure, I think, to the iterator interface, and it's certainly the first exposure to implementing an iterator. All right, so that's implementing an interface. Now, what if you want to make your own interface? Right. Okay, so to create an interface, it's easy, right? You just declare the interface like you would declare a class, right? Except you change class to interface, and away you go, right? And that's it. Everything in an interface is public, right? Even if you, even if you don't include an access modifier, everything's public, right? The interface is public. The methods in the interface are public. If there are fields, the fields are public, right? If you try to mark them as anything other than public, the compiler will issue a compile time error, right? So everything you put in an interface is public by default, right? And you cannot make it anything else, which makes sense because the interface is supposed to be the public interface to the, is supposed to be a public interface, right? It's supposed to be all of the methods and fields that some other class can use. Okay, so let's make an interface. So this is the simplest possible interface that I could come up with. I want to make an interface called printable, right? An object, a class that implements the printable interface, well, you can print an instance of that class, right? Note that it says this is not a very useful interface, and it's not. The only purpose of showing you this interface is to show you how to make one, right? So how does it look? Well, it's public. It's an interface, so it has to be public. Right? It's an interface, so it says interface, and then it has a name, so it's called printable. Right? And then you have the braces. Okay, what goes inside the braces? Well, the methods go inside the braces. Okay. So add your method declarations for your interface. Now remember, the interface methods usually have no implementation, so it's just the method with a semicolon. Right? So what's my one method in my interface? Well, it's public void print, right? Which, when you call that method, will print this object to standard output, right? And you know exactly how this is going to work, right? So that's going to call print. That's going to basically that's basically going to do system.out.println on the object, right? Which is why this is not a very useful interface. Okay, so there's my interface. Now you can easily make a class implement this interface. Right? So for example, suppose I want to be able to print all point2 objects by calling the print method. Right? So now I don't have to do system.out.println point. Right? I can just write p.print, and away we go. Right? So if I want to instrument the point2 class so that it becomes a printable object, right? Our current point2 class already implements comparable. Right? Now I want it to implement printable. Right? So a class is allowed to implement multiple interfaces. Right? There's no limit to the number of interfaces that a class can implement. Right? Next week, you'll see why this is important. right? But for now, it's just something that you should remember, right? Class can implement multiple interfaces. There's no changes inside the point2 class other than I have to implement print, right? So I override the interfaces method, right? And all I'm going to do is call toString on my object and then pass that to print line, right? And that's it. In fact, this is what you'll always do for the print method, right? And that's it. So now when you make a point, you can just write p.print and it'll print out the standard output. Right? If you wanted to, you could make the interface a little fancier, right? You could add another method that prints to, instead of standard output, you could make it print to what's called standard error, right? So that's the stream where you send error messages to, right? So to do that, you would have another method called public void print error or something like that, right? And then here, you would just have to figure out how do you send something to standard error, right? But that's it, right? So it's really easy to make an interface. Okay, where is this all heading? So this is all heading towards data structures, basically. Stacks. So I don't think I've talked about a stack yet in this course. That's a stack, right? So these are real life examples of stacks, right? You got a stack of files, you got a stack of books, you got a stack of pancakes, right? Everybody knows what a stack is, right? In computing science, there's something called a stack abstract data type, right? So the stack represents a stack of elements, right? And there's a notion of the top of the stack, right? So that's the book that's on top of the stack. So in the stack data structure, the only way you can access elements in the stack is via the top of the stack, right? So in other words, you cannot reach into the middle of the stack and pull out an element, right? You can only work with the element at the top of the stack, right? So classically, a stack supports only two operations, right? So it's about as simple a data structure as you can make. You can only do two things with it. You can push an object onto the stack, right? So pushing an object onto this stack would add another book on top of the stack, right? And then you can pop an object from the top of the stack. So popping removes the object on the top of the stack and hands it back to the caller, right? If you try to pop an empty stack, that's normally an error, right? So if you pop an empty stack in Java, you would throw an exception, right? And that's it. That's all you can do with a stack. Now, if you're going to make a real stack, it's useful to have some other methods. So it's useful to know how many elements are in the stack, right? And it's useful to know is the stack empty or not, right? Okay, so what does push look like? So I'm going to start with an empty stack, right? No stack. If I push an element onto the top of a stack ST, right? So I'm going to push the string onto this stack of strings, right? Then that's a picture of your stack, right? You've got a stack of size 1. It's got the letter A in it, right? Top points to the top of the stack. There's only one element, so it points to that element, right? If you push another object onto the stack, right? That's like putting something on top of the stack, right? So now B appears on the top of the stack, and the top moves up, right? Push C, right? C ends up on top, top moves up, D, and then E, right? So I now have a stack of 5 elements, right? Notice that the order that you've put things into the stack, right? I started with A, then B, then C, then D, then E, right? Notice that they're in reverse order when they come back out, right? So the last thing you put into a stack is the first thing that's going to come out, right? So when I pop, well, pop removes the top element of the stack and returns it to the caller, right? So I can pop the stack and store it in the string S, right? So S is now E, right? And then the top moves down, right? If I pop again, S is now D, S is now C, S is now B, and now S is A, right? If you try to pop again, you get an exception because there's nothing in the stack, right? Okay, now, why am I telling you about stacks? So it turns out they're used very widely in computer science and computer engineering, right? So if you've ever used the undo feature on your program of whatever it is, so either Word or PowerPoint or whatever program you're using, right? If you've ever used undo, That's implemented using a stack, right? So when you undo a command, right? So when you do a command, the command is pushed onto some stack. It's pushed onto the undo stack, right? You do another command, that pushes in a command onto the undo stack, right? Do another command, it pushes the command onto the undo stack. When you hit undo, you pop the element off the undo stack and undo the command, right? If you have a redo stack, then whenever you undo something, that gets pushed onto the redo stack, right? So all this undo redo, it's all stacks. A lot of low-level computer science involves reading files, right, or reading text of some kind, right? So reading and interpreting text is called parsing. Well, reading text is called parsing, right? It turns out a lot of parsers use a stack, right, because the language that you're parsing has some sort of structure that's amenable to using a stack to figure out whether or not the text that you're reading is valid for that language. Right? So a lot of computer programming languages, the parser in your compiler are stack-based. Right? Java actually uses something called the call stack. So the virtual machine stores information about any methods that are currently running in the call stack. And then finally, hopefully you've done some recursion in CISC121 or CISC101, probably 121, hopefully. Right? So you know that you can write methods recursively, right? You should also know that there's a limit to the size of a problem that most recursive methods can solve, right? But you can always convert a recursive method into a non-recursive one, and you can do it using one or more stacks, right? Because languages like Python and Java, they use a call stack anyway internally. So you can actually emulate the call stack by yourself using a plain old stack, right? To implement a recursive method, to turn a recursive method into a non-recursive one, right? And there's a whole bunch of other applications of when you'd use a stack as well, right? Your computer, your CPU actually has hardware stacks built into it. Okay, so these are all a little bit abstract, right? So instead of trying to do something like implement an undo stack right now, right? Let's do something silly, right? So suppose I want to reverse a list, right? Here's the way you can do it using a stack. Now you shouldn't do it this way, but you could do it this way, right? So here's a method that reverses a list using a stack, right? Notice that the method uses an interface, right? So it uses the name of an interface. This will work with any list, right? It returns a new list, right? The list that's returned is that list in reverse, right? So if you have the list ABC, I'm going to return the list CBA, right? Okay, so how does this work? Well, first I make a list to return, right? That's my result. Then I make a stack, right? What do I do with the stack? Well, I just loop over the original list, right? So for each string S in the original list, I'm just going to push the strings into the stack, or onto the stack, right? So now I've copied all the elements from the original list and put them into a stack. And then while the stack is not empty, right? So while there's something on the stack, I'm going to pop the stack, and I'm going to add the element to the result, right? And I claim that that reverses the list, right? Now why does that work? So there, T is the original list, right? I start with an empty stack, and I start with an empty list called the result. Right? What do? I take all the elements from T and push them onto a stack. Right? So I push the A onto a stack. Right? I don't take them out of T, right? I just loop over the list T. Right? So I push A onto the stack, then I push B onto the stack, and then I push C onto the stack. Right? Now, while the stack is not empty, I'm going to pop the stack and put it into the result. Right? So I'm going to pop the C and put that into result. I'm going to pop the B and put that into result, and I'm going to pop the A and put that into the result, and now your list is reversed. Right? So the stack is what's called a, Right? So the stack is what's called a LIFO data structure, last in, first out. Right? The last element that you add is the first element that comes out. Right? The second element that comes out, the second last element that you add is the second element to come out. and so on, and so on. Right? The first element you put into the stack is always the last one to come out. Okay, now how do you go about implementing a stack? So first of all, the Java standard library has a stack class in it. It turns out the stack class that's in it is not a very good one. Right? So we'll look at that, I think, in a lecture or two. Right? Now, if you wanted to make your own stack class, right, you can make the following observation. Right? So number one, the stack actually looks a lot like a list. Right? So if you kind of turn the stack on its side, right, so take that stack and turn it sideways 90 degrees, right, then that looks like the list ABC. Right? Every time you push something into the stack, right? So every time I push something into the stack, I'm just adding to the end of the list. Right? So I add the B to the end of the list, I add the C to the end of the list. Every time you pop something from the stack, you're just taking something out. Right? You're just removing the last element of the stack, the last element of the list. Right? So once you make that observation, implementing a stack becomes trivial. Right? You make your stack class, right? And you put a list inside your stack class. So inside my stack class, I'm going to have an array of strings, a list of strings, right? So this will be a stack that can hold strings, right? Later on, a couple of weeks, we'll make a stack that can hold anything, right? But for now, we're only holding strings, right? What does the no argument constructor do? Well, it initializes the fields, so it makes a new list, right? What does size do? It returns the number of elements in the stack. So that's just the number of elements in the list. Right? So that's just the size of the list. Right? What does push do? It adds an element to the end of the list. Well, that's easy. Right? Add the element to the end of the list. Right? Now, for an array list, that has complexity big O1 normally. Right? Every once in a while, it has complexity big O(n), where n's the number of elements in the list. Right? But most of the time, it's big O1. Right? So array lists are very fast. Right? Computationally, they're very efficient when you add and remove from the end of the list. Right? What does pop do? Pop removes the element from the end of the list and returns it back to the caller. How to remove from an end of a list? Well, you pass in the index of the end of the list. Right? What's the last element in the list? It's the size minus 1. Right? So that removes the element in the list. That always happens with complexity big O1 for an array-based list. Right? And that's it, you're done. There's your stack class. Right? Okay. That was pretty easy, right? I think everybody here could actually do it with a little bit of time. Right? If I told you put in a list and then add and take things out from the end of the list. Right? Okay, but there are other ways of implementing a stack. Right? So here I used an array list. Right? Instead of using an array list, I could use a plain old array instead. Right? So I can use a plain array to hold the elements. Now, the disadvantage of that is arrays have a fixed size. Right? So if the stack becomes very large, I have to make a new array, copy all the elements from the old array into the new array, right? So that I have more space for the elements. Right? So that seems like a disadvantage, but that might actually be faster than using the array list class. Right? There's another alternative. So you can use what's called a linked structure. And we're going to look at that in a lecture or two. Right? So this one's a completely different way of implementing a sequence of elements, right? That most of you probably haven't seen yet. Right? So we're going to create a linked structure where the elements are linked to one another. Now, both of these implementations, they have their own advantages and disadvantages. That's not exactly true. Right? The advantages and disadvantages are very small in this example. Right? They're going to become much bigger when we talk about lists. But for stacks, the advantages and disadvantages are relatively small. Right? But there are, right, the three different implementations will have different trade-offs and advantages. Right? So what you can do in this situation is you can make an interface for all stacks. Right? I can now implement a stack in all three different ways. Right? And then I let the user pick which one they want to use that's most appropriate for their purposes. Right? That's why the Java language has an array list and a linked list class. Right? Most of the time you use array list, but every once in a while you really want to use a linked list. right? It's why it has hash set and tree set, right? Most of the time you want a hash set, but every once in a while it's really useful to have a tree set, right? So you can have different implementations of a data structure that have different advantages and disadvantages, right? By providing all of the implementations and an interface to go along with them, right? You can let users pick the most appropriate implementation, but they're all programmed using the same interface, right? So if they decide later on, oh, I picked the wrong I picked the wrong implementation, they just change the implementation that they used, and none of their other code changes because everything was done using the interface. Right? And so that's really what the power of interfaces are. Right? And so I'm going to show you how to implement the stack in the next class, those two different ways. Okay? But for today, I think we're done. Yep. Any questions? All right. See you on Friday.